Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 47, part C. We're continuing our discussion of the moment generating function distribution technique, and this is a transformation technique. Okay, so in the previous videos in this section, we've looked at the MGF transformation theorem, and we've looked at a corollary that went with that, along with some examples and some significant results. And last time we looked at the theorem from the book, which is a little more complex in that it talks about the linear combination of independent random variables and using the MGF technique. And we have a corollary which is going to be proved during homework. So let's continue with some examples. So example 6, we have n IID, standard normal, random variables. And we want to find the distribution of the sum of z squared. Now, we learned earlier that if z is a standard normal distribution, then z squared has a chi-squared distribution with 1 degree of freedom. So all n of these random variables are independent and identically distributed with a standard normal distribution. So every zi squared is going to have a chi-squared 1 distribution. Now the MGF of the chi-squared distribution, since it is a gamma distribution with degrees of freedom, r over 2, and theta equals 2. So this is a gamma. In this case, since it's 1, it's 1/2, 2. And so here's our theta, which is 2. And then our alpha is going to be the 1/2 here. And so this is our MGF. And remember that t is less than 1 over theta, which is 2. So the MGF of W is m of w, and so we use our theorem, the product of m of t, they're IID, so we don't have any i's, so this is basically the corollary for the first theorem. And so this product is equal to m of t to the n, and so we take 1 minus 2t to the negative 1/2 and raise it to the nth power. So we multiply exponents and we get 1/2 or 1 minus 2t raised to the negative n over t, and t is less than 1/2 for our MGF. And this is the MGF of a gamma distribution. In fact, it's the distribution of a chi-squared, or the MGF of a chi-squared distribution with n degrees of freedom. So W is a chi-squared with n degrees of freedom. Our next example, so again, these are important results. Please write down your results. If Z1 to Zn are IID standard normal, then W equals Z1 squared plus Z2 squared up to Zn squared has a chi-squared n distribution. Now let's look at example 7. So we're going to let x1, x2 up to xn be independent random variables with marginal distributions that are normal with mu I as the mean and sigma I squared as the variance of each individual random variable. And we want to find the distribution of the sum of xi minus mu I divided by sigma I squared. So to rewrite this a little bit, I can rewrite this as xi. I'm just, instead of writing it kind of sloppy here, I'm going to rewrite it as a proper fraction. So mu I quantity squared over sigma I squared. And so I can rewrite that again as I equals 1 to n xi minus mu I over sigma I quantity squared. Okay? And so remember that we use z as our substitution for xi minus mu I over sigma I. And then w becomes, by substituting this in for this expression, then we have w is the sum of the zi squares. Now, I have here the MGF of the normal, but we don't really need that because we've already proven what zi squared is. Remember that zi is a normal with 0, 1. We showed that back when we talked about the normal distribution in Chapter 3, that if x has a normal mu, any mu, so I could call it mu I, and sigma I squared, then z equals x minus mu I guess I should call that xi minus mu I over sigma I, has a normal with 0 and 1 for the variance, mean of 0 and 1, so which is the standard normal. So the z transformation, if you have a normal distribution and you make this z transformation, the resulting distribution is a standard normal, and that's what we do to solve the problems using the z-table, is we subtract the mean and we divide by the standard deviation. And we showed that this squared, so z squared, has a chi-squared with 1 degree of freedom. So now we're going to do that, and we prove that using the transformation theorem in section 5.2. So the MGF is the MGF of a chi-squared distribution. So we're going to, of any zi here, so any zi squared, so I should say zi squared, has a chi-squared with 1 degree of freedom. Now, that means that the MGF of w, because all of these are independent chi-squares, so we take the product of m of z of I of t, and this is the MGF for a chi-squared distribution. Remember, theta equals 2. It's a gamma with theta equals 2, and alpha equals r over 2. And I believe I've left out a half here. And so it's a chi-squared 1, so r equals 1, so alpha equals 1/2. And so this is going to be 1 minus, so when I take the product of all of these, I take the product of 1 minus 2t raised to the negative 1/2, I end up with 1 minus 2t to the negative n over 2, and that is so now I have, this is the MGF for a gamma, and alpha is n over 2, and theta, because it's a chi-squared, equals 2. Okay? And so remember that this n, whatever's in the top of the fraction here, is the degrees of freedom for the chi-squared. So this is the MGF for a chi-squared with n degrees of freedom. All right. So we have just used this theorem to prove that if we have a independent normal distributions with any means, any variances, they don't have to be the same, but they're independent, then if we take each one of these variables and subtract their mean and divide by their standard deviation, so we transform them into a z variable, which has a standard normal distribution. When we square a standard normal distribution, we get a chi-squared distribution. And previously we proved that when you add up independent chi-squared distributions, that the sum of their you add or sum their degrees of freedom to get the chi-squared distribution of the sum. So S of n equals z1 squared plus z2 squared plus up to zn squared. They're all chi-squared 1, and there's n of them. So these are chi-squared n degrees of freedom. That's the resulting. And we've just shown that using the MGF method or technique here. Okay. So that's it for this video. Please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, please come to virtual office hours. If you need an answer before you can get to office hours, then by all means, please email me. But send me an email of the picture and of your work so far so I can see how you're approaching the problem. And then that will help me help you quicker through email. So please take care of yourself and stay safe, and we hope to see you next time.